Lagrange multipliers. Lagrange multipliers are used for solving constrained multivariable optimization. We're going to start with a word problem. We have a cylindrical can. There's a picture. It has a top and a bottom. And we want it to hold 1,000 pi cubic centimeters. The pi it's an odd volume, but that makes the problem work out easier. Find the dimensions that minimize the surface area. So we want to use the least amount of material. Well, we start with an objective and a constraint equation. The objective equation is what we want to optimize. Well, it says minimize the surface area, so it's going to be S equals. There are two parts to the can. If you cut this, get the top and the bottom off, cut it and unroll it, then the width of this is 2 pi r, that's the circumference of the top, times the height. So the circumference is 2 pi rh, plus the top is pi r squared, and the area of the bottom is pi r squared, so 2 pi r squared. Now the constraint equation, well, we're constrained by 1,000 pi cubic centimeters for the volume. So the volume of a can's area of the base times height, pi r squared times height, is equal 1,000 pi. Next, we want to build something called the Lagrange equation. Yeah, we're going to build a function. I'll call it f of r h lambda. Lambda is going to be a dummy variable that we insert into our equation. Well, we start with the objective equation, 2 pi rh plus 2 pi r squared minus lambda times the constraint. And just you have to move this to the other side, set it equal to 0, and it gives you pi r squared h minus 1,000 pi. That's what's called the Lagrange equation. We have the objective equation and the constraint equation. And this constant lambda, you can put plus lambda, it doesn't really matter, it just changes the sign of lambda. Next, we need to find three partial derivatives, f sub r, f sub h, f sub lambda, and we're going to set them equal to 0. F sub r, we'll start with this term, 2 pi h plus 4 pi r. And then to differentiate this part, you can just say minus lambda and differentiate inside the parentheses. And that gives us 2 pi rh, and we're going to set it equal to 0. And then we have f sub h. Okay, the h derivative of that is 2 pi r. H derivative of that is 0. Minus lambda, the h derivative of that is pi r squared. And we set it equal to 0. And then we want f sub lambda. This drops out. And we get minus pi r squared h minus 1,000 pi set equal to 0. This last derivative is always really the constraint equation in disguise. But this actually comes from two gradient vectors being parallel. That's where the equation comes from. But the third equation, you can just copy the constraint equation up here if you wish. Now what we need to do is solve for all these three variables. We don't really need lambda. Sometimes we solve for it, but Sometimes we don't. But we're really looking for R and H. And R and H, it turns out, will optimize this. So let's get to work doing some algebra. First of all, this equation here, you'll notice there's a pi you can divide out. And there's also a 2 you can divide out. So let's divide 2 pi into this equation. And that gives us h plus 2r minus lambda rh equals 0. Okay, we scaled it down right off the bat. Next, what we're going to do is solve for lambda. And we get lambda is, you can move this term over here, divide by RH, h plus 2r over RH. Next, we're going to, same thing, simplify this. You can get rid of pi, you can get rid of r. We know r is not equal to 0. r equals 0, obviously, is not going to optimize things. That would give us a volume of 0, which is an impossible situation. So you can divide by pi, divide by r, and we end up getting 2 minus lambda r equals 0. Okay, and again, you can solve for lambda. And we lambda, bring this over here, divide by r, you get 2 over r. And you can simplify this if you want. You can get rid of the pi, and that gives us r squared h equals 1,000. Okay, next what we do, you normally set these lambdas equal. That's a very common. The algebra tends to go in one direction. Set these two equal, we get h plus 2r divided by rh equals 2 over r. And then we can cross multiply hr plus 2r squared equals 2rh. Subtract 2r squared equals rh. You can divide by r. H equals 2r. There's an interesting relationship. That tells you that the height is equal to diameter. So the proportions are, from the side, it's going to look like a square. So that tends to optimize things when you have a cylindrical can. So if you go to the grocery store, a big can of baked beans, that's optimal. A little can, little pop can, for instance, not optimal. But there's other considerations. We want somebody to be able to hold it. So h equals 2r. Now, if you want the dimensions, guess what? We can put that together with this equation here. We have r squared h equals 1,000. Okay, r squared times 2r equals 1,000. Okay, r cubed is equal to 500. R is cube root of 500. Okay, it's some weird number. And h is 2r. H is equal to 2 cube root of 500. Those are actually the dimensions that minimize the surface area. So you can calculate that with a calculator. I don't particularly care what it is. We can, if you want the surface area is 2 pi rh plus 2 pi r squared. Okay, if you want to know how much sheet metal we need, 2 pi times r, which is equal to cube root 500, and h, which is equal to times 2 cube root 500. plus 2 pi, and we're right here in the formula. And r squared, r is equal to cube root 500 squared. And we can simplify that, I suppose. There's 2 pi times, this is actually cube root of 500 squared. If you want to simplify this before you go to a calculator, we have 2 pi times that squared. 2 pi times 2 is 4 pi times that squared. I guess we get 6 pi cube root 500 squared. And then whatever that happens to be, that's 500 to the, I mean, I could probably simplify it. 500 to the 2/3 power, whatever that happens to be numerically, times 6 pi, that's the actual surface area. So, okay, that's all for Lagrange multipliers for now.